Okay, so this is the textbook that we are following, and then see here, all these portions we have completed. Okay, so we have described wave, we have defined wave, right, and then we have represented wave in a graph of displacement versus distance. Not only by the graph of displacement versus distance, we also represented wave by displacement versus time. And then after that, we found out the wavelength, we found out the amplitude, we found out the frequency, right? And then we found out the frequency with the help of CRO, cathode ray oscilloscope. Then we discussed about different types of wave, and then on the basis of the direction of the propagation of wave with the direction of the vibration of the particles, right? So there were two categories. One is Lenzien wave, and then there is transverse wave. What are these waves we have defined? And then how we can represent the Lenzien wave, right? And how Lenzien wave can be represented in this form, okay? By the graph displacement versus distance. That also we discussed. And then after that, we discussed about phase difference, okay, intensity, and then wave speed. And then today, in today's discussion also, this topic will come, okay? The relation between the frequency, velocity, and the wavelength. Today also will be, again, reviewing on this relationship, the relationship between frequency, velocity, and wavelength. V equals F lambda, okay? Today also we'll use that relation. And then we did the Doppler effect as well, all right? Today also we'll have a certain review on the Doppler effect, okay? Then after we are done with all these, we are finally here in electromagnetic wave. So today's lecture will be focused on electromagnetic wave, and then here everything has been summarized here, okay? It has been condensed to a few paragraphs. So I would not like to go to each and every terms in detail, but just only go it surfacely, okay? And then we'd like to go it surfacely with the help of the simulation. It will help us to visualize something much more clearly. And then all these topics you'll be again studying while you go to A2, okay? So whatever the topics that we are going to go surfacely today without any depth, all these topics you'll be studying in A2, so do not worry. And then do not try to understand everything today, okay? Because you can't, and then we can't do it in this lecture, okay? As these topics that we are going to discuss will cover a larger portion in A2, okay? So you'll be studying in A2, we'll just go surfacely, and then we'll take the help of simulation. And then after that, we shall again go for the relation, as I said, the relation between the velocity, frequency, and the wavelength, okay? And then after we are done with this one, if we get the time, then we shall do the numerical problems as well, okay? Question 11 and 12. Okay, so this is how our lecture today is. Okay, so this is how we are trying to proceed to our lecture today. First and foremost, we'll understand something that we'll be studying in depth in A2. Today we'll do it surfacely. Then we'll understand what in my electromagnetic wave and what in my light, okay? Then after understanding that one, we shall try to find out a velocity of light in different medium, okay? And then we shall also study about the Doppler effect related to light. So these are the three objectives of today's lecture. So first of all, let us start with the definition itself. We'll be starting with the definition of light, okay? So light is what you see now, right? So it's daytime, then you will find the lights, okay? So this light, the light that's coming from the sun, okay, this light that's visible to us, okay, what is it actually that we are going to define it? And while we are defining it, as I said, there are some terms that will be really harder for us to understand in this level itself. So I like to go a surface level, give the simulation. So let's start with the definition of light itself. Okay, you can write down this one. Okay, it's given in a book, and let's start our lecture with this definition itself. Then we'll try to understand. Okay, for 1/3 of our lecture, we'll try to understand what actually we mean by light. Okay, so this is one of the objective to understand, though in surfacely. Okay, though we won't go in depth, we'll be studying this one surfacely, but we'll try to understand what light is as the first objective of today's lecture. So here, light is a wave known as electromagnetic wave that can travel through the space, including vacuum, as a disturbance of electric and magnetic fields. So light has been very nicely defined here, and then they say that the physicist has defined light as a wave. So here, so light has both the nature. Okay, again, so this is really harder to make you understand within this one lecture because it encompasses a lot of physics that we have to study. What I'm trying, okay? So please listen properly. So here it says that light is a wave, and let me tell you that light sometimes behave as a wave, and light sometimes behave as a particle. Okay, so light sometimes shows the property of reflection, refraction, interference, diffraction, polarization. So these all are the characters or are the characteristics shown by the wave. And as light reflects, refracts, okay, as light diffracts, as light interfere, and as light can be polarized. So all these are the properties of a wave. So we can consider light to be a wave. But another interesting theory through which Einstein got a Nobel Prize was he found that light is a particle, okay, and then it's a discrete packet of energy, okay, it's a discrete packet of energy, that's known as photon, okay. So and then he got the Nobel Prize on that. So here, light shows both the property of wave and that of particle. So it shows a dual nature, okay. And then here, as we are studying wave, so we are trying to categorize light as a wave here. So light is a wave. That means it shows different sort of phenomenon that's shown by wave, like reflection, refraction, then interference, then diffraction, and polarization. Okay, so the light also shows all these properties. So light is a wave, and then this wave is known as electromagnetic wave. So what is an electromagnetic wave? We shall go on to this one later on. Okay, and then if you see here, this electromagnetic can be just like here, this can be broken down into, or this we can break it down into two words, okay? One is electric and magnetic. So electromagnetic means both electric and magnetic, okay? So the combination of both electric and magnetic is known as electromagnetic. So light is a wave, and this wave is a combination of electric and magnetic field, okay? Or it's the disturbances created in electric and magnetic field. We shall discuss on that one later on. So light is a wave, and it's an electromagnetic wave. That is, it is the disturbance created because of the change in both electric and magnetic field, okay? And then this wave, or the disturbance that is created because of the oscillating charged particles, which furthermore creates the magnetic field. So I think it's getting heavier for you, right? So you can expect on that one. We shall understand that one later on with the help of simulation. So when the charged particle oscillate, then not only it creates the, okay, so here when charged particle is oscillating, then it will create the magnetic field. Okay, so charge has got the electric field. And then when this electric field is in oscillation, or when you say that the charge in oscillation, then it will create the magnetic field. And magnetic field in turn will create the electric field. So here, it's just like a chain. It follows a chain, okay? So first of all, the charge will oscillate. Please try to listen properly, okay? First of all, the charge will oscillate. We shall go through this one with the help of simulation, okay? Just try to understand. First of all, the charge will oscillate. As the charge oscillates, right, magnetic field is created, all right? And as there is the change in the magnetic field, again, it will create the electric field. And again, when the charge oscillates, again, it will create the magnetic field. And again, when magnetic field oscillates, it will create the electric field. So this goes on, okay? This goes on. So it's known as electromagnetic wave. And this electromagnetic wave can travel through the space, okay, including vacuum. So not only does it travel through the medium, it travels through vacuum as well. Okay, so it's known as electromagnetic wave, and it's different to that of sound wave. Okay, because sound wave requires medium, but this electromagnetic wave, that is light, doesn't require any medium. Okay, it can travel even in vacuum because there is continuous interchange between electric and magnetic and electric field. Okay, and then here as a disturbance of electric and magnetic field. So here, when there is a disturbance in electric field and in magnetic field, then this disturbance itself is known as wave, and this wave is electromagnetic wave, which is known as light, and this light can travel to the space. Okay, so first of all, let's try to understand how the oscillating charged particles will create the magnetic field. Then after that, we shall find out how the change in magnetic field will create the electric current, okay, or will create the change in the electric field. So after understanding about the definition, please listen to it properly. And if you find any confusion, you can ask me, okay? And then I'm telling you, everything is summarized, okay? And it covers a lot of portion of physics. In A2, you'll be basically studying about this one. You'll be studying about the quantum physics. You'll be studying about this one, magnetism, right? And then you'll be understanding about this one in depth. For today, I just want to go through surfacely. So please listen to it very attentively, okay? So here, light is a disturbance. Wave means what? It's a disturbance. And this disturbance is created because of the electric and magnetic field, okay? So here I'm producing sound, right? I'm producing sound. And then as I'm the producer of sound, this sound, okay, is being propagated up to you because of the disturbance in these air particles here, right? So air particles is in disturbance, and this disturbance in air particle will carry the sound that I'm producing from here up to your position, right? So similarly here, light is an electromagnetic wave, and that is produced, okay? That is produced by the disturbance of electric and magnetic field. Just like here, because of the disturbance of air particles, sound is being propagated from me to you. Similarly here, this light, okay, please try to understand, this light is disturbance. It's actually a disturbance of what? Electric and magnetic field here. Sound was propagated by the disturbance of air particles. Similarly, light is a disturbance of electric and magnetic field. And then here, this electric field will create the magnetic field, and magnetic field will create the electric field. How is it possible? That we are going to discuss it now, okay? So let's discuss here. Let's see the simulation. I think everyone is here. Please listen properly. If you have any question, you can ask me, okay? In the meantime, now let's go through some of the simulations that will help us to visualize it, because we can't understand everything in today's lecture, okay? So let's go it surfacely with the help of simulation. It will help us. So I think we have it. Okay, so here, first of all, we have got this one, okay? This one, here. Now here are the electrons, and electrons are charged particles, right? They are negatively charged, and these are the charged particles here. Now, because of the oscillation or vibration of these charged particles, let us say, because of the vibration of this charged particle, okay? And now here, these charged particles are vibrating. As you can see here, so they are going, see these motions here? They are vibrating, yes or no? They are vibrating, the charged particles are vibrating. So as the charged particles are vibrating, then see here, this is the magnetic field created. See here, see this compass? So this compass is being deflected, right? That means this compass will sense that in this region, there is the property called magnetic property, right? Or this region is a region where the magnetic field is observed, okay? So this will sense it, this compass will sense it. So see here, so when it flicks around, it suggests that here magnetic field is in presence, okay? Now here, these charged particles are vibrating. As these charged particles are vibrating, this magnetic field is being created. And why it is, do not ask me now, okay? In A2, you'll learn very nicely. Just take a surface, I am telling you. When these charged particles oscillate, then what happens? Magnetic field is created. Now let's take this DC. Here now, there is no any movement of the charge. So as there is no any movement of the charge, we don't find any magnetic field here. But on applying the voltage, then this charge starts flowing, right? This voltage will drive this charge, and then this charge starts flowing. And as the charge starts flowing here, the magnetic field is created. Now again, if I make this charge static, okay, if I make this charge static, no any magnetic field is created. Now, if I again make this charge move by applying certain potential difference between the ends of the wire, then we find the magnetic field is being produced. Okay, or here, if you can see here, because of the vibration of the charged particles, so here is to and from motion, because of the vibration of the charged particles, magnetic field is created. So one thing what you understand is that how will the electric field create magnetic field, right? So whenever the charged particles oscillate or vibrate, whenever the charged particles oscillate or vibrate, the magnetic field is created, okay? Now the next thing is we have to find out how magnetic field will create the electric field, or how magnetic field will create the current, okay? Will create the current in a certain circuit. That we need to find it out now. So here, electric field, the oscillation of electric charge creating magnetic field we understood. So here, when the charge oscillates, the magnetic field is created. Why? Please do not ask me now. We'll be studying in A2, okay? The next thing is here. Now we need to see how the change in magnetic field will set up the charge in motion, okay, in a circuit. How the change in magnetic field will set up the charge in motion in electric circuit that we are going to study. Now here, the charge is at static position. That means the charge is not flowing over here, right? And then this bulb will go only when the charge starts flowing here, right? So now here, now if I change the magnetic field, on changing this, on moving this bar magnet, so here, on moving this bar magnet, you'll find here the change in magnetic field, right? So these all are the visual representation of magnetic fields, okay? And they are imaginary though. But here, it will help us to understand very nicely, right? So here, I'm moving it. As I'm moving it, you can see the change in this magnetic field, right? This orientation of the magnetic field is being changed here, okay, as I'm moving it. So here, as we change the magnetic field, then what is it doing? It's moving this charge. Now here, as we change the magnetic field, we are changing the magnetic field, so the charge is in motion. Now, as the charge is in motion, please try to understand it properly, okay? As the charge is in motion, then again it will create the magnetic field. So here, the charge in motion will create the magnetic field, and the magnetic field in motion, and this magnetic field in motion will create the charge in motion. So here, again listen to me properly, okay? The charge in motion will create the magnetic field and the change in the magnetic field. So here, there has to be the change in the magnetic field, okay? And the change in the magnetic field will create the electric field. I think I'm clear now, right? So here, अगाडि के गर्यो? यो charge को यसलाई हामीले static राख्यौं भने, right? यसलाई हामीले static राख्यौं भने, if we keep it static, no any change in the magnetic field. But if we make the charge flow, then we can see here magnetic field, right? The magnetic field is created. Or if you see here, you see it is much more easier because of the oscillation of charged particle. Here we find the magnetic field, okay? And then see here, this magnetic field is changing. It's not static. See here, this magnetic field is not static, it's changing. And the changing magnetic field now, please listen to it properly. This changing magnetic field, now it's static. Now it has to change. Then only the charge starts flowing here, okay? And the change in magnetic field will create again the electric field. So here, the disturbance of electric field. So this one is the disturbance in the electric field. The disturbance in the electric field, right? See here, the disturbance in the electric field will create the magnetic field. And the disturbance in magnetic field will create the electric field, and it goes on. Now the disturbance in the electric field will again create the magnetic field, and the disturbance in the magnetic field will again create the electric field, okay? So it goes on, and then we'll find out this one. So here. So this magnetic field is changing. So here, this magnetic field is changing. As this magnetic field is changing, this electric field is also oscillating, or the charge is also oscillating. And as the charge is oscillating, again, this magnetic field will change, okay? Or magnetic field will be created. And again, when this magnetic field is changing, this charge will be oscillating, and it goes on. So here, the charge in oscillation will bring the change in the magnetic field. The change in the magnetic field again will bring the change in the electric field because of the particles oscillating. So it goes on, and this disturbance created because of the electric field that will create magnetic field, and magnetic field in turn will create electric field. This disturbance itself is known as electromagnetic wave. Okay, so that is what we defined here with the help of the definition. So if you go through our book, it has been very nicely mentioned here. So I'd like one of you to go through this one. So Mingma, can you please unmute yourself, Mingma? Mingma, are you there?
Yes, sir.
Yes, please, Mingma. Please read from here to here. Okay, please read this electromagnetic wave.
You should be familiar with the idea that light is a region of the electromagnetic spectrum. It is not immediately obvious that light has any connection at all with electricity, magnetism, and waves. These topics had been the subject of study by physicists for centuries before the connections between them became apparent. An electric current always gives rise to the magnetic field. This is known as electromagnetism. A magnetic field is created by any moving charged particles such as electrons. Similarly, a changing magnetic field will induce a current in a nearby conductor. These observations led to the unification of the theories of electricity and magnetism by Michael Faraday in mid-19th century. A vast technology based on the theories of electromagnetism developed rapidly and continues to expand today.
Thank you so much. Thank you. Okay, Mingma. Thank you. Now, after Mingma,
Thank you, sir.
thank you. I think you got it now, right? Did you get everyone? Did you understand? And did you understood the connection between the simulation and whatever we have studied just now? Did you or not? Please tell me. Is it clear? Or is there any doubt still? No one is talking. I don't know why. Okay. Now let me ask to Sandeep. Sandeep, can you please unmute yourself? Sandeep? Sandeep, are you listening to me? Okay. Let me.
Sir, I have network problem.
Okay. So Sandeep, what you do is, where was that? Now you read from here to here. Just like Mima, she has read the first paragraph. You read from here to here, from Faraday's. Go on reading.
Okay, sir. Faraday's studies were extended by James Clerk Maxwell. He produced mathematical equation that predicted that a changing electric or magnetic field would give rise to waves traveling through space. When he calculated the speed of this wave, it turns out to be the known speed of light. He concluded that light is a wave known as electromagnetic wave that can travel through space, including a vacuum, as a disturbance of electric and magnetic field.
Okay, thank you, Sandeep. Thank you. Okay, so here now, so just now what we found was that changing electric field, or when the charge is in motion, it will create the magnetic field, and when there is a change in magnetic field, it in turn will create the electric field. So these disturbances, okay, because of the disturbance in electric and magnetic field, disturbance will be created, and that disturbance itself is known as electromagnetic wave and is known as light. Okay, up to there we have discussed. And then here, so Faraday unified that one. Okay, so we can say this one, Faraday unified that one. By that mean, what you mean to say is that when there's a change in the magnetic field, then the current will be induced here. That is how Faraday related. So here, that's how Faraday related the current with the or the electric field with the magnetic field. Okay, so Faraday came up with a law that relate the electric field with the magnetic field, and you will be studying about Faraday's law later on, okay, in A2. So here, this phenomenon was given by the Faraday's law, and this phenomenon, by moving the magnet, okay, by moving the magnet, the current will be induced here as a result of which this bulb glow. Now here the bulb doesn't glow, right? Because this magnetic field is not changing. Now, when we change the magnetic field, okay, when you change the magnetic field, then the current will be induced here, because of which this bulb will glow. So this relation between the changing magnetic field and electric field was given by Faraday's law. Okay. Now from there onwards, Maxwell carried out his mathematical calculation, and then what he found was that a changing electric or magnetic field would give rise to wave traveling through space. So when there is a change in electric or magnetic field, then that change in electric or magnetic field will create a disturbance. That disturbance is electromagnetic disturbance, and that electromagnetic disturbance will travel through space. And then when you calculate the speed of these waves, okay, when you calculate the disturbances created because of the changing electric field or magnetic field, when you calculate the speed, it turned out to be the known speed of light, right? So the speed of light is 3.00 into 10 raised to the power 8 meter per second. So when we found that the wave that is being created by the oscillation of either the charged particles or by the fluctuation in the magnetic field, that disturbance will travel through the space, and that disturbance has got the speed equal to 3.00 into 10 raised to the power 8 meter per second, and that is the speed of light. Okay, so light is defined as an electromagnetic wave that is created because of the oscillation of either charged particles or magnetic fields. Okay, so this is how we came up with the definition. And it was rigorously studied, and the calculation was done, and it came nearer to the velocity of light. Okay, it was only it differed only to little extent, very less extent. Okay, so finally what they obtained is that when now here let's try to see this one. Now when this suppose this one is electric field, okay, or this is the field created because of the oscillating charge, okay, or let us say this is the field because of the charge. Now when the charges oscillate, then this will create the magnetic field, okay, and magnetic field in turn will create the electric field. So the disturbance either because of electric field, because when there is disturbance in the electric field, or when there is the oscillation in the charge, then magnetic field will be created. And when there is when this magnetic field fluctuates, then it in turn create the electric field. Okay, so either we can say the wave created because of the charge oscillation, or we can say the wave created because of the change in magnetic field. So these wave, okay, that is created either by the oscillation of charged particle or by the fluctuation in the magnetic field. The speed of that wave, or the disturbance came equal to the speed of the light, and then they found that light is actually an electromagnetic wave. Okay, so here this is electric field, and then these charges are oscillating. Along this vertical plane. Then this magnetic field, and this magnetic field is oscillating along the horizontal plane. Then the disturbance is traveling mutually perpendicular to these two. Okay, so here the wave is perpendicular to the electric field, the wave is perpendicular to the magnetic field, and electric and magnetic field are themselves perpendicular to each other. Okay, so all these three, electric field, magnetic field, and the wave, okay, they are perpendicular to each other. Electric field perpendicular to magnetic field, and then electric field perpendicular to speed, and magnetic field perpendicular to speed, says that electric field, magnetic field, and speed and wave are mutually perpendicular to each other. That means if the electric field is along the x-axis, okay, if the electric field is along the x-axis, the magnetic field will be along the y-axis. And if magnetic field is along the y-axis and electric field along the x-axis, then the wave or the disturbance will travel along the z-axis. So we have to have the concept of three axes. So if this represent the direction of electric field, okay, if this represent the direction of magnetic field, then the speed, then the wave will travel in another direction mutually perpendicular to this one, to electric field and to magnetic field, and electric and magnetic field are themselves perpendicular. So that means this and this are also perpendicular, this and this are also perpendicular, and this and this also perpendicular. Okay, so we finished our first objective saying that light is a wave, and this wave is known as electromagnetic wave. Electromagnetic wave means electric field creating magnetic field, and magnetic field in turn creating electric field, and that can travel through the space. So here, as electric field is creating magnetic field and magnetic field is creating electric field, they can not only travel through the medium, but they can also travel through the vacuum, and they are traveling as a disturbance of electric and magnetic field. Okay, so the first objective we have defined. Now let's go for the second objective. I think we have got, yes, 10-11 minutes, so I think we will be able to complete the second objective also. Okay, and the second objective of today's lecture is to know about this relation. So here we know this relation, right? V equals to F lambda. The relationship or the equation that is equating velocity, frequency, and wavelength is V equals to F lambda. We have already done this one. Now let's try to, let me ask one of our friend to read it, then we shall explain. Sunil, can you please unmute yourself, Sunil?
Yes, sir.
Okay, Sunil, what you do is you read from here to here, then again we shall go with the simulation and understand what does it mean, okay? So from when, we start from here.
When a light travels from a vacuum, from when to where, sir?
From you are on the right track, okay? When light travels from yourself, please go on up to here.
Okay, sir. Okay. When a light travels from a vacuum into a material medium such as glass, its speed decreases, but its frequency remains the same, and so we conclude that its wavelength must decrease. We often think of different forms of electromagnetic radiation as being characterized by their different wavelength, but it is better to think of their different frequencies as being their fundamental characteristics, since their wavelength depend on the medium through which they are traveling.
Okay, thank you. Okay. So thank you, Sunil. Now what has Sunil studied? Okay, let's try to understand that one. So let's just read this one first statement, okay? That first sentence that Sunil read. When light travels from a vacuum, so we're trying to see it visually, okay? The light is traveling from a vacuum with our simulation. When light travels from a vacuum into a material medium, and then we have got a glass, okay? Then what it says is speed decreases. Let's just try to find out with the help of virtual lab if this is correct, okay? So when light is traveling from vacuum into glass, the speed in the vacuum should be greater than the speed in the glass that we mean to say, okay? Because of which we can say that its speed decreases. And then the frequency remains the same. There's no any variation in the frequency though, okay? And we concluded that its wavelength must decrease, okay? So why the wavelength must decrease, we shall come up with this relation. First of all, let's try to understand, does it actually happen with the help of virtual simulation? Let us observe, is this written in the textbook, the right writing, or is it written incorrectly? Okay, let's try to find out. It says that when the light travels from vacuum to any medium, just like glass, the speed decreases, okay? Now let's try to find out with the help of the simulation. So here is our simulation, okay? Now see here, this is light, okay? It's a laser light. So suppose here, if this is a laser, and then this is the surface, okay? Here is air, and here is glass, okay? This medium is glass, and this medium is air. We don't have vacuum, so it's nearer to vacuum, okay? Only differs, refractive index of vacuum and air differs by, I think, 0.008 something, only on the third or fourth decimal places. So we can consider it to be just like a vacuum, okay? So here, light is coming. And then what you need to find out is the speed of this light. The speed of the light here is greater than here, okay? That is what we need to find it out, okay? And we can measure the speed with the help of this instrument. So here, we have got the instrument to measure the speed. Now, as you are studying light as a wave, so let's just bring a wave, okay? And it's a planar, the wave is in the form of plane. Why is it in the form of plane? We shall study in the second chapter, okay? Now, here, this is the light in the form of wave. And this light is coming from air and then going into the water, okay? And this is the boundary surface. This is air, this is water. Let's just make A. This is glass. So here is glass, right? Here is glass. So this is glass. Now let's try to see, as said by book, the speed of light here decreases. Let's try to find it out, okay? And then if we measure the speed here, let's just measure the speed here. So the speed here is 1.00 c. And then see, this is a, here it has been represented as a vector, and the length gives us the magnitude of this vector, okay, velocity, okay? The magnitude gives this length gives the magnitude of the velocity, and it is 1.00 c. Yeah, right? बुझै तिमीले कतिको बुझिरहेको छैन, कतै डाउट भयो भने सोधिहाल। यहाँ यो लाइटको स्पिड चाहिँ एयरमा कति रहेछ 1.00 c, and the value of c is 3.00 into 10 to the power 8 meter per second. That will be provided in a data book. No need to mug it up. The data book मा दिया हुन्छ। तर be careful, do not write down only 3. Do not write down only 3.0. Please write down 3.00, okay? Because it plays a role in writing a proper signaling figure. And then right? You change speed of light in air भयो. अब यहाँ आउँदा यो डिक्रिज हुनुपर्छ भनेर भनेको छ. So it has to be lesser than 1. Let's just try to find out if it is so or not. So is it lesser than 1? How much is it now? Can you please read it?
0.66.
Yeah, so it's 0.66 C. So it's lesser than 1. So here, velocity decreases here. The velocity decreases here. So that was what we discussed here in our textbook, right? So when light travels from a vacuum, okay, from air here into a material medium such as glass, its speed decreases, okay? Here the speed is decreasing. Obviously, as in here in this simulation, the speed is decreasing. But what remains constant is the frequency, okay? Frequency remains constant. So here, velocity changes. Velocity changes with the change in the medium. So here, now here is glass. Now let's put here water, what happens? Let's just try to find out, okay? If it is water, then let's try to find out. Now here, the velocity is changing. So when here is water, the velocity is 0.75 C, or if you place it here, when it's water, it's 0.73 C. When it is glass, it is 0.65 C. And when it is air, then just like if it is air, then here it is C itself, right? So here this velocity of the light is being changed, okay? It's changing on the medium through which it travels, okay? As the light travels through the medium, its velocity also changes. Please try to listen it very properly, okay? यो सबै कुरा अरू चाहिँ प्रोग्रामहरुमा जस्तै प्लस 2 मा यति धेरै यसलाई त एक दुईवटा लेक्चरै लगाएको छ तर हाम्रो यो लेभलमा एकदमै कन्डेन्स फर्ममा दिया हुन्छ त्यही भएर बुझ्नु चाहिँ पर्छ तिमीहरुले ओके ट्राई टु अन्डरस्ट्यान्ड सो हियर व्हेन इट इज एयर इट इज 1.00 C when it is water it is 0.73 C and when it is glass is so when it is glass let's find out here when it is glass 0.65 C so the velocity is changing. The velocity is changing as it passes through the medium, but one quantity doesn't change. And sometimes in your BE exam entrance preparation or in your MBBS entrance preparation or even in your SAT, right? When you give SAT, if you want to go abroad, then the question will be asked, what's that quantity, that physical quantity, whose value doesn't change when light travels from one medium to another medium? Then you have to answer it as frequency, okay? Frequency doesn't change, but the velocity changes. Now here, frequency doesn't change, velocity changes, then of course there has to be change in the wavelength. So please try to understand this properly, okay? Frequency doesn't change. So here, we know the relation between velocity, frequency and wavelength as V equals to F into wavelength, okay? Suppose this one lambda is wavelength. Now here, this changes, this fluctuates, okay? This fluctuates, it's not constant. This fluctuate, okay? It's not constant. This is constant. This is constant, okay? This doesn't fluctuate. This is constant. Frequency is constant. So does the wavelength change or not? Can anyone please tell? If velocity changes, frequency is constant. Does the wavelength change or not as it goes from one medium to another?
Yes, sir, changes.
Yes. So lambda also changes. Yes, of course, lambda changes. Okay. So here, velocity changes. Lambda changes, only frequency remains constant. So here what they have defined is it will be better if we can characterize the light on the basis of frequency, because frequency is that quantity that doesn't change as the light goes from one medium to another medium. When this light, okay, when this disturbance goes through one medium to another medium, suppose here is water, here is a glass, here is air, then its velocity changes, wavelength also changes, and only one physical quantity that remains fixed is frequency. So it will be better if we can characterize electromagnetic radiation on the base of frequency, because it remains constant. That is what is being said here, okay? In the paragraph read by Sunil, okay, the next paragraph. So here, यति धेरै कुराहरु हामीले एउटा सेन्टेन्समा लेखेका हुन्छ, so it's really harder, right? A level सजिलो छैन, एकदम गाह्रो हुन्छ है. So please here. Okay. अहिले जति पनि हामीले डिस्कस गरे यसलाई एउटा सेन्टेन्समा राख्दै छ, and then if you miss the sentence then you will be missed with the concept. So please go through each and every word of a textbook, okay? They are very much valuable. So here, and so we conclude that its wavelength must decrease. That's fine. We often think of different forms of electromagnetic radiation, okay? So there are different types of electromagnetic radiation. How many types of electromagnetic radiation we shall come later on in tomorrow's lecture, but listen to the sentence properly. we often think of different forms of electromagnetic radiation as being characterized by their different wavelengths. So generally, what we think is that the electromagnetic radiation, are being characterized by their different wavelengths. But it is better to think of their different frequencies as being their fundamental characteristics. So frequency doesn't change. So just if someone is fluctuating here, right? So someday one of you are interacting, and the other day if you don't talk, then I can't call you. And then if you're constantly interacting, I think that, okay, I'll have faith that you will interact, right? So I'll be calling you. Similarly here, as the frequency doesn't change, it will be better to characterize electromagnetic radiation on the basis of frequency rather than on the basis of the wavelength. That is what we have discussed. Okay. With this, we have come to the end of this
Excuse me, sir.
class. Yes, Sagat.
Sir, is a Doppler effect valid for electromagnetic radiation?
Yes, of course. And we shall discuss that in the next week. Okay. On coming week, we shall discuss on that one. Thank you for asking that question, Sagat. Okay. Thank you so much. Thank you, everyone. Okay, Pratik, if you have any question. Okay, Shreya, thank you.
Yes, sir.
Yes.
Sir, what if there will be the vacuum instead of water and glass, sir?
Oh, if there is vacuum, then the speed will be 3.00 into 10⁸ meter per second.
It's in constant, sir?
Yeah, it is equal to that of the velocity of light is greater in vacuum. Okay, and as the medium comes there, and as the vacuum is filled by air, similar to vacuum. If it is filled by water, if it is filled by glass, then the velocity decreases.
Okay, sir.
Okay, thank you, Pratik. Thank you so much.
Thank you, sir.